In example 3, we want to sketch the graph of this polar function r is equal to 2 cosine 3 theta. And we're going to talk about two different methods that we could do this. One way is going to be making a table, and the second way is going to be using parametric equations. So again, we are very familiar with graphing rectangular functions. For example, equations like this, where we would make a table, plug in x values, get out y values, and then we would take these points and we would plot them to see what that graph looked like. The first method is very similar to that. So instead of plugging in x values and plugging in theta values, I've gone ahead and picked theta values ranging from 0 to pi, and I would plug them into this function r is equal to 2 cosine 3 theta. So for example, when theta is 0, cosine of 0 is 1, so r would come out and be 2. And I went ahead and made a table for this and pasted this here because we're not really seeing if we know how to evaluate trig functions. So I've gone ahead and gotten that table filled out, and then we would just take these points and we would plot them. So for example, the point 0,2 as a polar point means that your angle is 0, so you're on the x-axis and you're 2 units away. So the point 0,2 is right there. Pi over 6, 0. The radius is 0, so you would sketch the angle pi over 6. But because r is 0, your point is just at the origin. So we've gone from the red point to the blue point. So we have this kind of pattern going on in there so far. Because remember, there are more points in between here. Because, for instance, you could have used, say, pi over 12 in between those two, and you probably would have gotten that point right there in the middle. Pi over 3, negative 2. So here's the angle pi over 3. But because r is a negative 2, you're getting this pink point back there. So now you've traced out even more of the graph so far. And following this same pattern, you continue to trace out petals of what is actually a rose curve. We'll talk more about that later. So kind of the same way that in rectangular equations, we call all second degree polynomials parabolas. All in polar equations, all equations that look like r equals some number cosine some number, those form rose curves. And here is one way that we could sketch this one. Alternatively, if we didn't want to make a table and plot points, another way that we could sketch this polar graph is we could use parametric equations. So we do know from switching to polar to rectangular, just what we know about the relationship of polar and rectangular equations that was covered in the first half of this lesson, that x is equal to r cosine theta and that y is equal to r sine theta. That's also coming back from Math 172 when you took trigonometry. So if x is r cosine theta and y is equal to r sine theta, in this example, r is 2 cosine 3 theta. So I'm going to replace r with 2 cosine 3 theta. There was still a cosine theta that's multiplied by. And for y, I'm again replacing r. I'm replacing r with 2 cosine 3 theta. And then there was still a sine theta that was multiplied by. So what that does is that has now given me two parametric equations, one for x and one for y. And I could combine these points and plot them as just regular rectangular XY coordinates. So these two columns of the table could be used to plot as XY points, and you would get the XY coordinates that we're getting in the schematic above and eventually end up with the same graph. So that's just showing you two different ways that you could graph this polar function. We just saw an example of how to graph a polar curve. In fact, the polar curve that we just graphed was an example of a rose curve, something like this. Now that we have a little bit more familiarity with what polar graphs look like, we're going to shift our discussion to talking about slopes and tangent lines of polar graphs. So just an idea of what we're doing, imagine that we have some kind of curve. For example, maybe it's a rose curve, so it is possible that the entire graph would look something like that, similar to what we saw in the last example. we may be given some point on that polar graph. And remember that polar points do look like r theta. And what we're trying to find is the equation of that blue tangent line. I remind you that the concept of what we're talking about now is exactly what we started Calculus 1 with. Calculus 1, we started finding tangent lines to graphs. Now we're doing the same thing, but in polar coordinates. So we just saw an example of how we can use parametric equations to graph polar coordinates. The last two columns that we filled out back in example 3. Finding these parametric equations for x and y, and plotting these rectangular points in order to see this polar graph. As a reminder, we formed those parametric equations by using the equations x is equal to r cosine theta and y is equal to r sine theta. And remember that r is simply the equation of our polar function. Now that we have those parametric equations, x is equal to f of theta cosine theta and y is equal to f of theta sine theta. We just replaced r with the polar function. We're going to use what we learned in section 10.3 to find the parametric form of the derivative of this polar equation. So in section 10.3, we saw that if you have parametric equations x and y, very similar to the two that we have here, well, not those versions, but rather these versions, then we can differentiate that using this here. We take the derivative of y with respect to theta and we divide that by the derivative of x with respect to theta. In the previous section, we had t as our parameter. It's just that here we're using theta. So let's just look really quickly at how I'm getting this dy d theta. Here's y, f of theta sine theta. If I want to differentiate that with respect to theta, I would need to use the product rule, because f is f of theta, this first piece, and g is sine theta. So f prime would be whatever the derivative of f with respect to theta is, and g prime would be the derivative of sine, which is cosine. So applying the product rule, we would have f prime g, which would be f prime multiplied by sine theta, plus g prime f, which would be cosine theta multiplied by f of theta. Very similarly, we would do the same thing with x, which is the product of f of theta and cosine theta. So we would need to apply the product rule again in order to get this denominator here for the derivative of x with respect to theta. So now that we have a representation for the derivative of a polar function, we got that using parametric equations, we can make some observations. So remember, this entire fraction here is the representation for the derivative. So when will the function have a horizontal tangent line? Well, we know, generally speaking, from Calc 1, that we get horizontal tangent lines when the derivative is equal to 0. And I'm going to change my notation. We get horizontal tangent lines when the derivative is equal to 0. The derivative is a fraction. Fractions equal 0 when the numerator is equal to 0. The numerator is dy d theta. So we will have a horizontal tangent line when the derivative of y with respect to theta is equal to 0. When will we have a vertical tangent line? Well, we know from Calculus 1, vertical tangent lines have undefined slope. That means that the derivative would be undefined. The derivative is a fraction. Fractions are undefined where their denominator is equal to 0. The denominator is dx d theta. So we will have vertical tangent lines when dx d theta is equal to 0. Do note that if both are equal to 0, then we cannot make any conclusions about the tangent line. So now that we have an idea of how to find horizontal and vertical tangent lines to polar graphs using the parametric representation of that polar function, let's look at example 4. We want to find where the polar function r is equal to sine theta has horizontal and vertical tangent lines. First, let's just get an idea of what does the graph of r equal to sine theta look like. So I'm scrolling up to the graphic that includes polar functions, and you will be given this graphic on the final exam. R equal to sine theta looks like a circle. A is 1 in our case, so it's a circle with a diameter of 1. Notice that that circle is sitting on top of that polar axis. So that looks something like this. I do know that this rectangular coordinate is 0, 1, rectangular. Remember, this entire diameter of this circle is 1. So this goes no further right than 1/2 and no further left than -1/2 on the x-axis. There's my y-axis. But remember, we are working in polar coordinates, so I don't want you to focus too much on the x and the y coordinates. I put them down there to give you some perspective. Just another point for perspective, this circle is centered at the rectangular coordinate 0, 1/2, because remember its diameter is 1. But we're looking for horizontal and vertical tangent lines. We can see that the graph has 2 horizontal tangent lines, one at the top of the circle, one at the bottom of the circle, and 2 vertical tangent lines on the left side and on the right side. What we're going to be looking for in this problem is what are the polar points, or theta, where this graph has these vertical and horizontal tangent lines. So we should have 4 answers in total, 2 for the blue vertical tangent lines and 2 for the horizontal red tangent lines. So let's get started with writing the parametric equations, because remember, to do this, we need this representation of dy d theta and dx d theta, because it is where dy d theta is equal to 0 that we will have horizontal tangent lines, and where dx d theta is equal to 0 that we will have the vertical tangent lines. So I'm going to begin by writing expressions for x and y, using the fact that y is equal to f of theta sine theta, and x is equal to f of theta cosine theta. I will be replacing f of theta with sine theta. This r is our function f of theta. It's like the same way that when we're in rectangular coordinates, y is equal to f of x, r is equal to f of theta. So replacing f of theta with sine theta, we would have sine theta multiplied by sine theta. To see that y is sine squared theta. Going to do the same in x. I'll replace f of theta with the function sine theta. So I simply get that x is sine theta multiplied by cosine theta. Now that we have the parametric equations for both x and y, we can now differentiate them with respect to theta. So now I'm going to take dy d theta. I want the derivative of sine squared with respect to theta. I would need to use the power and the chain rule. Just to give you some perspective, we're thinking of this function. So I pulled the exponent of 2 down. The new exponent on sine is 1. I don't typically write that. Chain rule says we have to multiply by the derivative of sine, and the derivative of sine is cosine. Now to take dx d theta, we're going to need to use the product rule, where f is sine and g is cosine. So f prime would be cosine theta multiplied by g would be cosine squared theta. G prime would be a negative sine theta multiplied by f, which is sine, would be a negative sine squared theta. So now we have differentiated both of these functions with respect to 0. We now need to figure out when is dy d theta equal to 0. Because when dy d theta is equal to 0 is where we will have our horizontal tangent lines, and when is dx d theta equal to 0. So at this point, we now have trigonometric equations to solve. This is going back to 172, solving trig equations. This trig equation, it's already factored. This will equal 0 when sine is equal to 0. And when cosine is equal to 0. Remember that we are working on the interval from 0 to pi. So you're thinking about where on the unit circle, this is the unit circle here, going back to 172, from 0 to pi is either the x-coordinate or the y-coordinate equal to 0, where cosine is equal to 0 up here at the angle pi over 2, because the x-coordinate is 0. And sine is equal to 0 here at the angle 0, because the point is 1, 0, and the y coordinate is equal to 0 here. So our solutions here are theta is equal to 0 and pi over 2. Now let's go solve our blue equation. When is dx d theta equal to 0? When is cosine squared theta minus sine squared theta equal to 0? Equation, I'll add sine squared to the other side. I'm looking for where cosine squared is equal to sine squared. I can square root both sides, but when I square root both sides, we do need a plus or minus. So we're looking for the angles between 0 and pi where the x and the y coordinate on the unit circle are either the same, like they are at pi over 4, or where they have opposite signs of each other, like they do at 3 pi over 4. So we have found 4 angles, which is good because we know from just what the graph of r sine theta looks like that we're looking for 4 different points where we have these horizontal and vertical tangent lines. So now let's go find the corresponding r values so we can finalize what these 4 points are. So in conclusion, we know that we have horizontal tangent lines when theta is equal to 0 and when theta is equal to pi over 2. So let's just make a quick table. Theta r when theta is 0 and when theta is pi over 2. Remember that r is equal to sine theta. So r in this case would be sine of 0, which is 0, and then sine of pi over 2, which is 1. So the 2 points that we're getting are the points 0, 0. Remember, this is r theta, and 1 pi over 2. So here is our point 1 pi over 2. And here is our point 0, 0. I'm talking about the polar points. Polar point. So that 1 pi over 2 is go to an angle of pi over 2 and go up 1 unit. Notice that that does correspond to the rectangular point 0, 1 that we already had labeled. Finally, let's go find where our vertical tangent lines are. We know those angles are pi over 4 and 3 pi over 4. Let's go evaluate what the corresponding r values are. Remember that r is equal to sine theta. Sine of pi over 4 is root 2 over 2. You could use my little mini unit circle as a reference. And sine of 3 pi over 4 is also root 2 over 2. So now we have these last 2 points. This is at an angle of pi over 4 and root 2 over 2 units away from the pole. Root 2 over 2 pi over 4. And our last point was root 2 over 2, 3 pi over 4. That's this point over here. Go to an angle of 3 pi over 4, root 2 over 2 units away. So these 4 points are our answers for where the graph has horizontal and vertical tangent lines. In example 5, we want to do the same thing and find the horizontal and vertical tangent lines of the graph r is equal to 2 times the quantity 1 minus cosine theta. Before I get started, again, I want to give us an idea of what this graph looks like. I'm going to show you how you could graph this on a graphing calculator. For example, if you're working on the final exam and you want to graph a polar function to make sure you have an understanding of what it looks like to help you find where these tangent lines are. On the calculator, after hitting mode, you would switch from function mode, which it's very likely already in, to polar mode. And once you're in polar mode, when you hit y equals, you're now entering your polar equation in terms of r. So notice it says r equals. So I'll go ahead and type the function that we have. Notice that when I hit x, I do get a theta. And I'm going to hit window next because I want to make sure that I am letting theta run from 0 to 2 pi. And I'm going to first just graph it on a standard window because that's how it'll look most of the time when you hit graph if you haven't zoomed in, which I'm going to do now. I'm going to hit zoom 2 to zoom in a little bit. Notice that I've zoomed in a little bit too much. I can't really see the left side of it. And when I zoom out, this is what I see. So now I'm just going to adjust my window slightly so that I can have a better idea of what this function. So I just played around with the window a little bit to get some values that work for me. And now I have a good idea of what this polar graph looks like. And this is helpful because now I can see that in terms of horizontal tangent lines, I'm looking for 2 points at the very top and the bottom of this polar graph. And for vertical tangent lines, there's a point here where there's a vertical tangent line, another point there with a vertical tangent line, and a point here with a vertical tangent line. You may be wondering, well, what about this point right here? That's giving us a cusp, that little indentation on the graph, there, that's something that's called a cusp. And we will dive into what is happening at that point in the theorem that follows this example. So to find my horizontal tangent lines, I need to work with the parameterization for y. Just using what we know about polar coordinates to rectangular coordinates, we do know that y is equal to r sine theta. In this case, r is 1 minus cosine theta. So I've replaced that, and this is still multiplied by sine theta. We will need to take the derivative of this function with respect to theta. I'm going to use the product rule where I think of this piece as my f and this piece as my g. Better yet, I'm going to go ahead and just keep the constant of 2 in front and just take this 1 minus cosine theta to be my f to simplify. So here is f multiplied by g prime, and to that I will add g multiplied by f prime. I'm going to go ahead and multiply out on the inside. And then I will apply a Pythagorean identity. So let's talk briefly about why I applied that Pythagorean identity to that sine squared. Remember what we ultimately want to do. Our goal here is to figure out where does dy d theta equal 0? Because that's the points. That's going to give us the theta values for where this polar function has these horizontal tangent lines. So if ultimately I'm trying to figure out where this is equal to 0, I'm solving a trigonometric equation. Again, you have to think back to 172. If you were trying to solve this trig equation, you would not like the fact that you see both sine and cosine in that trig equation. So what would you do? You would try to rewrite the equation with only one trig function. Would you try to write everything in terms of sine, or would you try to write everything in terms of cosine? You would try to write everything in terms of cosine because this cosine is not squared. So you cannot use a Pythagorean identity on that cosine that I underlined in gray. So you would use a Pythagorean identity on the sine term. So now this expression only has cosine. It's quadratic in cosine. We know how to solve quadratic equations. So ultimately now we have something that we can factor and solve this equation. So I'm going to continue to clean this up. To help me factor this, I'm going to go ahead and factor out a negative so I can see a positive coefficient to my cosine squared. When I factored out a negative, I need to be careful because my signs will change. And the 2 is still in front of that cosine squared. So now at this point, think about the algebraic equation. -2, 2x squared minus x minus 1. How would you solve that? You would factor that quadratic on the inside, and that quadratic would factor into 2x plus 1, x minus 1. So this factors into 2 cosine theta plus 1 cosine theta minus 1. And then we can solve by setting both of our factors equal to 0 and see that we're looking for where is cosine theta equal to a negative 1/2 and where is cosine theta equal to 1. So now we can use our knowledge of the unit circle because we know that cosine is equal to negative 1/2 where we have an x coordinate of negative 1/2 on the unit circle, which is at the angles 2 pi over 3 and 4 pi over 3. And cosine is equal to 1 on the unit circle at the angle of 0. So we have found three angles where we have possibly a horizontal tangent. To go find where we have vertical tangent lines, we're going to need to work with x. So the parametric equation for x is x is equal to r cosine theta. I will replace r with the value or the expression given. I'll go ahead and simplify this expression. So now that we have a simplified expression for x, we can now differentiate this with respect to theta to get dx d theta. We will need to use power and chain rule on the second term. Now we have this equation. We want to know where this equation is equal to 0. We're interested in where is dx d theta equal to 0. If I were setting all of this equal to 0, I would factor out sine theta, and I would also factor out a 2, which would leave me with 2 cosine theta. I switched the order of my terms, minus 1. Setting both factors equal to 0, we're looking for the angles where sine is equal to 0 and where cosine is equal to a positive 1/2. Those angles are 0, pi, pi over 3, and 5 pi over 3. I do want to be clear, notice how the angle of 0 is showing up as a solution for both dy d theta equal to 0 and dx d theta equal to 0. That means that we cannot conclude what is happening in terms of a tangent line when theta is equal to 0. Now I'm going to go back to the original equation and use this to get the actual points that we have here. So I'm going to set up a table of theta values and r values. The first theta value we found was 2 pi over 3. That was when dy d theta was equal to 0. I'll plug that into r. And this comes out to give us a value of a positive 3. That is this point right here. Here's the angle 2 pi over 3. We moved 3 units away from the pole. This line segment right there is 3 units away from the pole. So we have a horizontal tangent. I'll start writing my final answer. We have a horizontal tangent. I'll write this in red to stay consistent. We write these points as r theta. R is 3 when theta is 2 pi over 3. Let's go see what's happening at the angle 4 pi over 3. Mind you, 4 pi over 3 is down here in quad 3. Looks like r is going to be 3 there as well. And it is, because cosine of 4 pi over 3 is a negative 1/2. 1 minus a negative 1/2 is 3/2, and 3/2 times 2 is 3. So we also have a horizontal tangent at 2, 4 pi over 3. Those are the two red tangent lines that we saw in the graph. Notice how we're not concluding anything about 0 since it showed up for both the dy d theta and the dx d theta. Let's go get the points in blue for the angles that we found from when dx d theta was equal to 0. I'll start with the angle of theta equal to pi. I'll plug that into R, and we get out 4. That is this point right here. Notice this is the angle pi, 180 degrees. That is 4 units away from the pole. So one of the 3 points where we have a vertical tangent is the point r theta for pi. Let's go find the other 2. Let's move on to the angle pi over 3. I'll substitute that into r. We get out an answer of 1. So the angle pi over 3 r1, that's this tangent line up there. We have the point 1 pi over 3. And then finally, when we substitute in our last angle from when dx d theta was equal to 0, we get out 1 as well. So our final point is 1, 5 pi over 3 for where the graph has a vertical tangent line. Finally, we have a theorem that states if we take a polar function and evaluate it at some angle and get 0, so if we can find a 0 of that polar function that does not make the derivative of the polar function equal to 0, then the line theta is equal to whatever that angle is must be tangent to the graph at the pole. So we can use this theorem to find tangent lines of polar functions at the pole. Let's see this worked out in an example. So here we have the polar function f of theta is equal to 2 cosine 3 theta. And we're interested in what are the tangent lines at the pole of this function. So I'm going to begin by first finding the zeros of this function. So I'm going to set f of theta equal to 0. So I'm solving the trigonometric equation 2 cosine 3 theta equals 0. So this is taking us back to 172. I would divide both sides by 2. I'm looking for the angles where cosine 3 theta is equal to 0. Well, I know that cosine is equal to 0 at pi over 2 and 3 pi over 2. So I'm looking for where 3 theta is equal to pi over 2 or 3 pi over 2. Which would give me that theta is equal to pi over 6. Or pi over 2. But we have to remember that we have not dealt with the fact that the period of this cosine 3 theta is 2 pi over 3. So if the period is 2 pi over 3, then there's more solutions within the first revolution of the unit circle. That means that I could take the solution of pi over 6 and add 2 pi over 3 to get another solution. This would give me 5 pi over 6. If we took the solution of pi over 2, and added the period of 2 pi over 3, we would get 7 pi over 6. But we've seen this function before, 2 cosine 3 theta. We looked at it earlier in this lesson. It is a rose curve. And we saw in the first example that we looked at where we graphed a polar function that this entire rose curve is traced out by letting theta run from 0 to pi. So I don't need any solutions that are larger than pi. So I'm not going to consider the 7 pi over 6 because that is larger than pi. I'm only considering the pi over 6, the pi over 2, and the 5 pi over 6. So now that I have my zeros, let's evaluate the derivative, because this theorem says that all three of these zeros will give us tangent lines at the pole if they do not make the derivative equal to 0. The derivative of 2 cosine 3 theta is negative 6 sine 3 theta. You should quickly be able to see that when you evaluate this at pi over 6, you do not get 0. When you evaluate this at pi over 2, you do not get 0. And when you evaluate this at 5 pi over 6, you do not get 0. Please do take the time to work through all three of those evaluations to make that conclusion. Now that we have this, we can conclude that there are tangent lines, 3 of them, and they are the tangent lines theta equal to pi over 6. Remember, the theorem tells us the lines. The lines are theta equal the angle. Theta equal to pi over 6, theta equal to pi over 2, and theta equal to 5 pi over 6. And the last thing I want to show you is that these answers do make sense considering that we know what the rose curve looks like. Here's the rose curve that we graphed originally. The tangent lines that we're seeing are the lines when the angle is pi over 6 at the pole. That green line is at an angle of pi over 6. Or if the angle is 5 pi over 6, I'm going to come in and hit tangent at the pole right there. Tangent at the pole, so I'm talking about the origin of this system. There's my tangent line at 5 pi over 6. The one in green was just pi over 6. And then finally in red, here's the tangent line we found on that third petal when theta is equal to pi over 2 with the angle of pi over 2.